Recording again? Okay, so now we are back to chemical properties. Um, some of the words that really stand out to me when it comes to chemical properties is the like ability of something. You're going to have a change taking place at like the molecular or atomic level. Okay, now we're going to go from there. Chemical properties. Usually, whenever it comes to identifying or distinguishing a chemical property from a physical property, there's some words that you want to look out for. Burns, rots, explodes, decomposes, ferments. All of these terms, you know, if you think about water going from an ice cube to its liquid state, how would you describe that? The word, the technical word, and the word that anyone's going to use is, well, it melts or it freezes. You're not going to say, oh, that water burnt or that ice cube burnt. If it did, well, then your water's contaminated with something you definitely don't want to drink it. Um, but look out for, when it comes to chemical properties, look out for these sorts of words. In addition to that, say you want to add on to their rusts. And really, you could throw in their ability. Ability to. That's a good stem that you want to look for as, okay, this is how we see a transition or we see something happening. The ability of metal to, react with acid or something like that. Okay, so now we've got our next poll question. Here we've got some examples of chemical and physical properties where we are looking at, um, okay, good. We're looking at gallium melting at 30 degrees Celsius. Mercury is a very dense liquid. Gold is shiny. These are all physical descriptors. Iron metal rusts. A green banana turns yellow when it ripens. A dry piece of paper burns. That is one that people get hung up on because I, I don't know why, but whenever somebody says like a piece of wood burns, or a piece of wood transitions to a pile of ash, well, you're changing its physical appearance, sure, but the chemical composition is also changing. And I think some of those things will become a little bit more apparent as we learn more about what's happening and we get a little bit more, or we get some more tools in our tool belt. So here's our next poll question. For those of you who are using the mobile app, I hope that you can kind of sort that out. And just so everybody knows, um, we did not have any poll questions on Monday. And today, since today's kind of like it's almost like we're getting our bearings about ourselves. Um, Everyone's going to get full credit for participation today and Monday. Because I want you guys to start out with like a stable ground to stand on. And, I know that I just had a technical issue. I know that everyone's kind of adjusting to technical changes and figuring out, okay, this is the best way for me to answer a poll question. Okay, so we've got a good number. We've got 70. I'm going to stop right there. We got 106 responses, and the results, we had an overwhelming percentage, 71%. The vast majority of the class answered that it was a chemical change. So the key word here is ignites. If something, that was put as if something ignites. Now, I want you to make sure that you think about that word. Like whenever I think about it, ignite or ignition, I think about a couple of things. One, I think about a lighter, and you have the metal scrape against the flint, and that causes a spark. Well, that spark is going to cause a gas like butane, which is your common gas in a lighter. It's going to cause that to ignite. Now that butane, that's a organic compound, and it's going to burn. So then we're going back to one of those those key words there for a chemical change, burns. Okay, now when it comes to neither physical nor chemical, both physical and chemical, those are, I would say, most of the time, the questions that I ask about these sorts of changes, I'm going to be as narrow as possible so that I'm describing one or the other. So if I were you, I would go ahead and operate under the idea that both physical and chemical is probably not going to be the answer. And that's kind of a test taking strategy question for this class. Okay, next up, we've got classification of matter. So this is our new stuff. Now, for classification of matter, I'm going to bring up another poll question. We've got a solid, a liquid, and a gas. Well, I think everyone can kind of think about a solid, you know, this coffee mug here. That's solid. What is inside of it is a liquid. Okay. So when you're thinking about this coffee mug, for instance, you know, I'm guessing that it's mostly aluminum. And if I, strip the paint off of it, well, and I expose that aluminum to a very high temperature, what do you think would happen to that aluminum? So imagining that I got the paint off of it, it would melt. You're absolutely right. Now, one thing that I want to, and here's where I'm getting at, I'm going to try to narrow the scope as much as possible, is that, well, if I didn't remove the paint and I threw it in a high heat, well, that paint, that would probably burn. But the aluminum itself, that's going to melt. So that will go from a solid to a liquid. And then if I got it to an even higher heat, what's going to happen to that liquid? It's going to go to a gas. I would not want to be in the presence of aluminum gas because that's going to be at such a high temperature. So I'm going to end the poll. And we got about 89% saying that it was a physical property. So a state, a physical, or a state, a solid, liquid, or a gas, that is a physical property. Great job, everyone. Okay, so when it comes to characteristics of states, these are things that you want to think about. And I know somebody, appropriately so, is going to be like, wow, it's a very tacky example. Um, but I'm going to jump right over here, far right hand side, gases. A gas is going to have an indefinite shape and it's going to have an indefinite volume. So if you think about do I have a soda bottle around here? I don't. I don't have a soda bottle or a soda can or anything like that. But if you look at a soda can, it's going to have a designated volume, a specific and defined volume. So that means the space that it occupies. Whereas a gas, okay, and a gas, and whenever I was in sixth grade, there was a girl who brought a stink bomb to school. And she went to the bathroom at one point, and a stink bomb is like a little glass vial that has a liquid in it. And whenever you break it, well, then it produces a hydrogen sulfide, and that smells like rotten eggs. So she went to the bathroom, broke it off, and let's think about this. That gas, or that liquid converted to a gas, so we had a physical change there. That gas then filled the bathroom. Okay, so if you were in the bathroom, it stank. I don't know, it stunk. It smelled horrible. Okay, then could somebody add to the chat what's going to happen as that gas basically fills the bathroom? Let me ask you, does the bathroom have any like connection to any other part of a building? Okay, it diffuses, yeah. Let's think about our air conditioner, our duct system. Yes, gas is going to take up more space. And if there's an opening in that bathroom or in that container, what's that gas going to do? It's going to diffuse, it's going to exit. So when I was in sixth grade, and this girl broke this stink bomb off in the bathroom. It filled the bathroom. The gas filled the bathroom. And then, Haley, you're absolutely right. It traveled. It went into the ductwork. And then it went down the hall or down through the ductwork to the other parts of the building. Initially, that gas's volume was the bathroom, but then it expanded, and that gas continued to expand. This is when I was in sixth grade, and by the time we got to lunch, the odor had filled the entire building because the gas had no defined shape and no defined volume. I mean, it would get to it, it'd be like, okay, well, it's going to fill whatever container that it's in. That container was first the bathroom, then it was the bathroom plus the ductwork, then it was the bathroom plus the ductwork plus every single classroom. And you know what that was for every sixth grader? The best day of the year. The reason is it smelled horrible. And we laughed about it because that was funny. But then it was elevated to the best day of the year because the odor was so strong that it wasn't really a safe environment for us. So what happened? School buses came. We got to go home early. And that girl's name was like the best kept secret until one of my friends found out and told on her. Anyway, so gases. Gases have no defined shape. Whatever container they are in, exactly. You're right, Emily. Gases are going to fill whatever container. If that container is this cup right here, and that cup has a lid on it, the gas is going to fill that. If you take the lid off, the gas is going to fill the entire room. Now, liquids. Well, liquids don't have a defined shape. Liquids will only have a defined shape of, well, what they're in. So if I took this cup of water, and I poured it on my desk, is the shape that the water has right here in this cup going to be the same as when I pour it on the desk? Not at all. It's going to spread out. And then I'm going to spill on my user manual for my smart ring that I bought. So that's not good. Now, a liquid, however, will have a defined volume. That defined volume is, well, whatever container that it's in and the total amount of space that it occupies. If I take this cup and I pour the water onto my tabletop here, well, could I calculate the volume that it occupies? Yeah, it's going to be hard, but I could. And that volume is going to be equal to what it is in here. Are the shapes going to be different? Yes. Are the volumes going to be different? No. The only way the volume would be different is if I do this. I've reduced some of that volume. Now, great question, Dan. Yes, plasma is a state. We don't go into plasma though, because of the fact that it's not really relevant to this class. If I remember correctly, plasma is like a physical chemist's realm. Like I said the other day, I'm more of a biochemist. And there you have what are called, I think it's ionized noble gases. So the conditions that are required to make a plasma or that plasmas take on are different. And in terms of these different variables, I believe that they're somewhat similar to gases because they don't have a defined shape or volume. But that's a great question, Dan. And I hope that my answer is adequate. Okay. So last but not least, solids. Whenever I think of a solid, the first thing that comes to my mind is a brick. Just like a masonry brick, used to build a house or something like that. What do I think about whenever I think about a brick or a cinder block or something like that? It has a defined shape. That shape is whatever the mold was. It has a defined volume. The only way that that volume is going to, well, I mean, heck, if you got a brick and you were a black belt and you broke it in two, does the volume change? No, you have two pieces of a brick. They both combine to equal the same volume. So a solid has a defined shape, a defined volume. Liquids have, I kind of look at this almost like a progression. Um, Solids have two of two things that are defined. Liquids have one of two things that are defined. And then gases have zero of two things that are defined. Okay. Now, question number 5. And what we have here is how we kind of organize things. So in just a second, I'll post the poll up there. Um, every piece of matter, everything can be organized in this fashion. Here, what we have are a solid gold walking liberty coin. Here, what we've got is water. This would be brass or bronze or something like that. And then this would be a ring or rings that are both bronze and it's kind of tough to see here, silver. Okay, so everything can be categorized kind of using this flow chart. Get a material, get a piece of matter. Is it a substance or is it a mixture? A word that's omitted here, pure substance. Now, this is a little bit of a preview for your next poll question, but the water that's in here, well, it's from the tap. Okay. Tap water has a bunch of stuff in it. It's got minerals, it's got compounds like sodium chloride, it's got in Central Texas. Does everyone know what is in um, water in Central Texas? A lot of makes it hard or soft. Calcium, not fluoride, calcium. Um, Calcium does, like calcium containing compounds are what make your water hard or soft. And I grew up in Central Texas and I never really noticed anything. Then I went to visit some of my relatives in Washington State and I was like, their water, it feels weird. And well, it's because they have very soft water where they lived. And I was like, oh, interesting. Pure substance. Tap water is not a pure substance. So tap water is an example of a mixture. Now, pure substances can either be an element. This would be solid gold, or they can be a pure substance, a pure solution of water would be right here. Now, launch a poll question. Back. Poll result. Oh, right back. Apparently, I'm sharing a poll result still. Stop sharing. That's my parenting advice that I always give my kids. Stop sharing. Okay. Pure water is kind of gave a little bit of a clue there with pure water is a leading answer there. Okay. Water is a pure substance. Sometimes whenever you see one of my questions and my poll, I'm going to share my result. When you see a question, pure water is, I'm not really doing that to be a decoy and like throw you off. Okay. So just kind of anticipate that. So that's how we can organize and categorize things. Mixtures we can categorize as homogeneous or heterogeneous. If you look on the right hand side here, we've got a heterogeneous mixture where we've got bronze and maybe a white gold or something like that. And so this, the way that I always kind of think about a heterogeneous and a homogeneous substance is what does it look like at the macro level? Like this cup right here. This cup, well, it's pretty uniform. It looks the exact same. If I were to look at it right here or right here or right here, it's going to basically look the exact same. And that indicates that it is a homogeneous material. Sorry. Now, we can also categorize things as elements or compounds. Now, this is where we're venturing more into kind of chemistry and where it can get kind of tricky and get kind of hairy. So be patient with this and be patient with yourself on learning this. Elements are things that are composed of one type of atom. That's not to say that it's a singular thing, but here what we have is I think that this is the word for gold. Maybe that, no, that's silver. I was going to say an ignot. Um, but if you had a gold bar, well, that's just thousands upon millions of this element. So you could kind of think about it as like AU. And I'm sorry, I have to do this, but that's my AU. That's the way that you talk to people. AU. That's gold. So it's lots of these individual atoms of gold bunched up next to one another. That is one type of atom. Now, we'll get into what constitutes the differences between these. Gold is a metal, and so it's all these elements that kind of exist together and organize in this specific way. Oxygen, or O2, is a gas, and so that is oxygen atom and an oxygen atom. Two of them come together to make one molecule. Now, one thing that can be kind of tricky is, well, a compound versus a molecule. And I want you to not think about compounds and molecules. Instead, compare a compound and an element. So a compound is composed of two or more elements. So a fair question is oxygen, is O2 a compound? No, it's not. It's an element. Now, looking at this, here's your poll question. This is an important thing to think about because lots of what we do in this class and in chemistry in general is lots of we use lots of different symbols. So, what color is used to represent an oxygen atom? We've got red spheres and we've got white spheres. Your answer options are red, gray, and white. Hey, we'll go ahead and end the poll right there. And you're absolutely right. The majority of y'all, 75%, got red is the correct answer. And you're right. Gray wasn't an answer option, and the only other answer option was white. And those white spheres are going to be. Does anyone want to add to the chat and guess? What do the white spheres represent? Hydrogen. Perfect. Okay. Now, next up. Here's where we bring in the term molecule. A molecule is composed of two or more atoms. Ooh, I gotta jump back. Aha, there's a difference here, and there's an important difference. A compound is two or more elements. A molecule is two or more atoms. So an atom is the smallest characteristic part of an element. So an atom is kind of a representation of the atoms or the elements that we see on the periodic table. Now, so keep that in mind. A molecule is composed of two or more atoms. So here we've got water, H2O, Carbon dioxide, CO2, again with the red spheres representing our oxygen. And then last but not least, O2. It's our two oxygen atoms. Now, I brought this up a little bit ago. Organization, categorization. That's what chemistry is a lot of. Analyzing something and kind of categorizing it, sorting things out. So, tap water, that's our poll question right here. Tap water is a mixture or a pure substance. Now, this kind of flow chart right here is really helpful. So I think that as you're kind of planning out your scratch guide for your exams, right now you might be like, "Ooh, I'm going to put that table on there. I'm going to put this flow chart on there." But as we work through this material, you'll probably gain a little bit more comfort and be like, "I don't need to put that on there." So, tap water, is tap water a pure substance? No, it's not. So immediately we got to go down this path. Okay, then thinking about tap water, is it going to be homogeneous or heterogeneous? And whenever I think about answering that question, I'm going to go ahead and stop the poll, share the results. We got 93% of the folks said that it was a mixture. You're absolutely right. Now, whenever it comes to is it heterogeneous or is it homogeneous? The way that I think about it is if I get my glass of tap water, and this is a cup, but if I get a glass of tap water and set it on the counter and leave it there, Lisa, homogeneous. You're absolutely right. My rationale is if I leave it sitting on the tabletop for, 8 hours, 2 weeks, 3 weeks, whatever, if I just leave it sitting there and then I come back, is that tap water going to basically look the same? Yeah, it is. Chances are slim that there's going to be a bunch of junk at the bottom of it. If there was a bunch of junk at the bottom of it, then I'd be like, ooh, that's a heterogeneous mixture because those two things separated from one another. Okay, so now talked about these are kind of our big dividers, elements versus compounds and atoms versus molecules. That's 1.5. Now we're moving on to 1.6, measuring matter. Okay, so we've got a couple of poll questions. Where did question? There it is. Which of the following is a molecule? And actually, I'm gonna skip that one. Um, yeah, so you guys probably did not see that one. What do we have for 9? Okay. This is one that, when it comes to measuring matter and taking measurements, I think that everyone has you've been exposed to taking measurements and you kind of have an understanding of them, but you haven't maybe put it into the terms that we're going to use. So here's one that I want you to think about. What is the international unit for temperature? Degrees Fahrenheit, degrees Celsius, Kelvin, nanodegrees Fahrenheit. As I'm watching the answers roll in, I see a bar graph and it's like, and then one ultimately kind of rises to the top. Okay, I'll give another couple of seconds. Drink the last bit of my now cold coffee. Yep, it was cold. Okay, so we're looking at 5 more seconds. And done. Oh, and the last person answered nanodegrees Fahrenheit. Proud of you. Solid answer. But, and I don't mean this, I don't mean that in a mocking way. I'm always just I like it sometimes when I see someone who's like, I'm gonna go with that one. And like I said previously, there's no consequences to getting the answer wrong. So, whatever. Okay, share the results. Maybe not overwhelming, but the majority of folks answered correctly with degrees Celsius. And that international is something that is important because we have in basically every type of measurement, we have common units. So if you're measuring the length of something, the international or the most common units throughout the world are going to be meters. Mass, grams. Volume is going to be liters. That's your base unit. If you're measuring time, it's going to be in seconds. Temperature is degrees Celsius. And I noticed that a lot of people did answer Kelvin. Well, Kelvin is also in the mix for temperature measurements. This is what a chemist is going to use. This is the chemists. I'll say chemists and physicists. And I'm going to spell physics because I don't want to misspell the word physicist. And then last but not least is amount of substance. Add to the chat if you've heard about or have heard of a mole as like an amount. I'm guessing most of the people who answered to the very first poll question of have you taken a chemistry class before? If their answer to that was yes, then their answer to this question is probably also yes. Um, Mole is the unit that we use in chemistry and in biochemistry to kind of compare amounts. So we will not get into moles until a little bit later on. I'm going to introduce a tad of it right now, but we'll get more into moles later. Okay, so the first thing that I want to do is I want you to look at this number right here. 1 mole is 602,000,000,000,000,000,000,000,000,000,000,000,000 particles. Now, I know from my own experience, a mole was something that like really frustrated the heck out of me. It's a concept that's tough to wrap your mind around because let me put it in terms that are a little bit different. Let's say hypothetically that you had 1 mole of US dollars. Okay. If you had that many dollars, do you have a lot of dollars? I'm going to say singles. I'm going to say 1 mole of US dollars. Great question. So effectively, yes. For the time being, what I'm going to do is I'm going to scribble this out. If I told you that you have 1 mole of US dollars, you have 602,000,000,000,000,000 word. Okay, 3333333. You'd have that many dollars. A pretty good number of dollar bills. If I had that many pennies, I'd also be fine with having that many pennies. And I don't mean this as a slight or as disrespect, but if I had that many dollars, I don't think we would know each other. Um, because I would have a lot of dollars. And there's certain islands that I would own, for instance, all of them. Um, okay, you're right, Troy. If I had that many dollars, I I'd throw some of you guys' way. I mean, the point is, I'd have a lot. You know what, Matthew? I'm fine with that. If I had that many dollars, I'd be cool. Like, if I had to give up 50% of those dollars, I'd be like, that's fine. I mean, anyway. So my point here is that this is miserable, probably, as, yeah, mo money, mo problems. Probably us, yeah, because I'd be a shell corporation, so I'd go Jeff Bezos style and be like, oh, hey, work hard, guys. That's what I did, not pay $0 in taxes. At any rate, I'm distracting myself, and I can't do that. So, my point is that this number is absolutely massive. It's tough to wrap your mind around. So that's at the heart of understanding what a mole is. Now, in order to make this a little bit more tangible or make it easier to process, and if nothing else, to not have to write out all those dang zeros, which I still don't know if I wrote out the correct number of zeros. I don't think that I did. We use something known as scientific notation. And that scientific notation drives what are known as our metric prefixes, our metric or our international prefixes. So when we look at numbers, 8675309, one, that's Jenny's phone number because that's the song. Jenny, Jenny, who could I turn to? By Tommy Two Tone was the band. Now, this is something that I'm going to pose it to you guys. And is that the one? No. We're going to come back to this question, but what I want to do is I want to ask you a couple of, or give you a couple of poll questions. We just did 9, so now we're looking at this. And think about this almost as a process. So just to answer this question, 2.4 times 10. Is it 24? Is it 0.24? Can it not be determined? Or is it 2400? 2.4 times 10. If you have 2.4 10 times. Not a trick question. This is just multiplication. I can give you about 10 more seconds. So 2.4. Handwriting was particularly bad right there. 2.4 times 10. I can go ahead and stop the poll. Share the results. 84% of y'all, or 85%, got it right. Okay, so 2.4 times 10 is, you guessed it, 24. Okay, now, question number 11. What is 10 squared, or 10 to the second power? That caret symbol, that's called a caret. 10 to the second power is the same as 10 squared. You're raising 10 to the second power. So this is the same as 10 times 10. What does that also equal given these answer options? I'm going to go ahead and end this poll right here and share the results. 93% said 100. You're absolutely right. I'm on the same page as you. And just so everyone knows, I'm going a little bit more quickly and cavalier with the times that I give you for your responses. I'm pretty uniform in giving you about 45 seconds to 50 seconds to answer the poll questions. So today, if I'm cutting it off, don't be like, oh no, I didn't get to answer it. For starters, everyone's getting credit for the first 2 days of class. And then this is a little bit atypical in terms of the pacing. So don't stress about it, please. Okay, question number 12. Now we're kind of putting it all together. If you saw this, this is our scientific notation, 2.4 times 10 to the second. We've got 2.4, 240, 24, 0.24, 24,000, infinity, or cannot be determined. About 5 more seconds. And scene. Okay, so our most popular result was 240. That's correct. So when you see that times 10 to the second, and I know that everyone kind of has boundaries of where they understand something and then where their understanding kind of alter or like changes a little bit. But when you see 2.4 times 10 to the second power, break that into pieces. Say 10 to the second. Okay, I know that that's 100. So 10 to the second, that's effectively 2.4 times 100. Okay, now it gets a little bit more complicated as that exponent increases. So 10 to the third. If you saw 2.4 times 10 to the third, well, that's 10 times 10 times 10, which is 1,000. But now let's go back to this. 2.4 times 10 to the second is the same as 2.4 times 100. Another way that you could think about this is, well, 2.4 versus 240. And I'm going to put a decimal right here. So 2.4 versus 240. Where is the decimal, or how would you describe the decimal? Is the decimal place in the, or is the decimal in the same place when you look at 2.4 and 240? Two places to the right. Okay, then I got a private message. Wait, so yes, that was a private message that said, so we can use PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, and use the exponent first. Yes, you do. So then what we can do here, Adriana, you're absolutely right. The decimals are not in the right same place. So if we wanted to describe how do we get our decimal, or how do we describe the difference between 2.4 and 240? Well, you move your decimal one, two places. What did our exponent say? It was positive 2. So if I wanted to write 2.4 times 10 to the fifth, go ahead and add to the chat what this number is. And you don't have to do all the calculations, but instead you can just look at your exponent and look at your decimal place. Add it to the chat. I got one response, 2.4. And then I'm moving my decimal 1, 2, 3, 4, 5. I'm doing the way that I always do this is I will write it out and then I'll put my zeros in because I know that I have to have zeros there because it's not like I have 1 or anything like that. And now I'm going to erase. Done. 2.4 times 10 to the fifth is the same as 240,000. Okay, I'm going to stop my share right there. And then, let's see, those are the questions I wanted to ask. So now let's go ahead and look at this poll question. Another poll question. Which number is the smallest? Now the answer options are different from, or no, they're the same, sorry. Oh my gosh. Are we gonna do it? Are we gonna do it? Nope. Close. 40 seconds. Or sorry, 40 seconds. When we hit 40 seconds, which is in about 5, 4, 2, 1, done. Share the results. I actually gave 44 seconds, but 96% of us said 0.00024. Okay. So then how would we take that number and make that or convert this number 0.00024, convert that into our scientific notation? This right here is sometimes and commonly known as full notation. So how would we, if we did 240,000, excuse my handwriting, if 240,000 is equal to 2.4 times 10 to the fifth. Oh, Adriana, Emma, great job. What would we do? Well, Thank you. Austin, yes, we do. We do. Absolutely. Okay. So if we are moving our decimal place, going from, I got a private message from someone who said, so negative exponent moves the decimal to the left. Yes, absolutely. So when we write this in, I'm going to say scientific notation, side note, we're going to say 2.4 times 10 to the, and this is where it gets a little bit tricky. Are you converting, and are you converting a number with a decimal place, or sort of, if you're going to scientific notation, one, two, three, four. We're going to say times 10 to the negative fourth. Now, one of the ways that I always think about this, and I make this easiest for myself, is I say, is the number in complete notation greater than or less than 1? Okay. And that's the basic question that I ask myself. If the number is less than 1, I use a negative exponent. Then, alternatively, is the number greater than? If the number is greater than 1, I use a positive exponent. Now, the key in all of that to make this kind of make sense is you've got to remember complete notation. You're thinking about the number in complete notation versus scientific notation. So anytime you see this exponent or this times 10 to the whateverth power, that's going to be your indicator that, okay, we've got this as a positive exponent. That means my number is going to be bigger than 1. So if you see answer options on a test or something like that, A, B, C, D. And I'm going to go ahead and erase this real quick. Here's my question. And this is the last thing we're doing today. 240,000 is blank in scientific notation. Okay. Okay. So I'm going to give you a couple answer options. We got 2.4. We've got 0.0000024. We've got 2.4 times 10 to the negative fifth. And then we got 2.4 times 10 to the fifth. Okay. So, Adriana, absolutely. Emma, absolutely. Now, what we can do is kind of go in process of elimination. We can look at answer option A. Is 240,000 the same as 2.4? No. I would rather have $240,000 bills than $2.4 bills. Therefore, if somebody ever comes up to me and they're like, hey, Joel, I see your stockpile of $240,000. I will trade you $2.4. I'm going to decline that trade. So, process of elimination, that's out. Then this right here, 0.0002 point or 0.00024. Ooh, that's tempting. There's lots of zeros there, and there are lots of zeros here. But this, well, is this number even in scientific notation? No. Get out of here. Answer option B. Okay, then we got C and D as answer options. And I know that lots of y'all had already answered the question and added the correct answer. Awesome. Thank you so much. 2.4 times 10 to the negative fifth. Ooh, that's an exponent. And D also has an exponent. But I always look at it if I, what I do, and this might sound silly, but if I am going to uh, taking from scientific notation to complete notation, whenever I see that negative, I always draw an arrow because that's the direction that I'm moving my decimal. Okay, so our correct answer, because C is out, our correct answer is D. Now, this is where we're ending today's lecture. So what that means is that the stuff that follows this will be picked up on Monday, not on Monday, next Wednesday, because Monday is a holiday. Um, I'll be sending out some announcements. You've got your quizzes that are due on Sunday night. I've got office hours on that link that's on our Canvas page, and I'll post the link also later today um, at 12:30. Other than that, I gotta say, I think this was a good lecture or good time. Thank you guys so much for coming to class. The group me's been added to the chat. I apologize for the computer issue that I encountered today. I hope you guys have a great day. I hope you enjoy your long weekend and don't get too cold. Thank you so much for coming, everyone. And I'm going to be posting our lectures, all of them to date, on our Canvas site later today. All right, everyone. Bye bye.